Hello and welcome. In this lecture, we are going to look at the flow of control in a program with function calls. Here is a quick recap of some of the relevant topics we have already studied. We have seen the use of simple functions in programs. Basically, a function encapsulates a computational subtask and allows us to do modular programming. We have seen how one function can be invoked from another function, and we have also seen that functions mostly return values of specified types. We have also looked at in some detail the contract centric view of programming with functions. In this lecture, we are going to see in great detail how control flows in a program when a function is called and when a function call returns, and we will see that this flow of control is implemented through activation records and call stack. So let us recall the encoding example that we had seen in an earlier lecture. We wanted to store the quiz 1 and quiz 2 marks of all CS101 students in an encoded form so that others cannot figure out the actual marks. The encoding strategy we had decided upon was that the ordered pair of marks m comma n will be encoded as 2 raised to m times 3 raised to n, and we are going to assume that all marks are integers in 1 through 10. Here is the C++ program structure that we had seen earlier. I have only written down those parts of the program where I want to focus. These are the parts with function calls. The other parts I have blanked out with 3 dots. So here in the main function I have a loop which is iterated for every student, where we read in the marks and then call this function myEncode, which takes 2 integer parameters and returns an integer value which gives the encoded version of these 2 marks. Now the function myEncode in turn calls a function power to raise 2 to the power of quiz 1 marks and 3 to the power of quiz 2 marks. So this is another function call within the function call myEncode, and of course power raises base to the exponent and returns that value. Now in the contract centric view of programming with functions, we said that we do not need to worry about the internals of a function when we are using it, and this is achieved by specifying preconditions and postconditions and respecting those whenever we call a function. Since this is very important in the use of programming with functions, let us recall the preconditions we had used there. We had said that quiz 1 marks and quiz 2 marks should lie between 1 and 10, and why did we say that? So that the result, which is 2 raised to quiz 1 marks times 3 raised to quiz 2 marks, can indeed be represented within 32 bits. And of course if this precondition is satisfied, this function guarantees that the return value is exactly as we expect. For the power function, we had a precondition base greater than 0, exponent greater than equal to 0, and I have also added another part to the precondition here. This is important, which we had not discussed in the earlier lecture, that the result base raised to exponent should lie between 1 and 2 raised to 31 minus 1. This is the range of positive numbers, positive integers that can be stored in the integer data type, and so we required this as part of the precondition, and if this precondition is satisfied, then the return value will indeed be as expected. Now let us look at how control flows in this program with 2 different function calls to myEncode and calls to power. So here is our little running man showing how the control is being executed in this function. We are inside the for loop and we have now encountered this function call. What do? We remember where to return back when this function call returns in some bookkeeping information, and then we go to the first executable instruction of myEncode, and then we start execution from there and we encounter power. Now this is the function call power, so again we have to remember where to return back from power and start executing the function power, the instructions in the function power, and after executing those instructions, when we hit return result, when we execute this instruction, we have to go back and look at this bookkeeping information to figure out where to return control to, and once we have done that, we do not need this bookkeeping information, we can proceed ahead with our execution of myEncode. We encounter this function call, again we keep track of where we should return back, come to power and start executing the instructions there. When we hit result there, we look up this bookkeeping information to figure out where to go to, then this bookkeeping information is no longer needed, and finally we execute the remainder of instructions, execute the return statement here, and now this bookkeeping information tells us where we should return to, so we return there, the bookkeeping information is no longer needed, we now execute the remainder of the instructions. Now this is a for loop, so I might go back into the for loop and execute the loop one more time. So as you will see, we are keeping track of bookkeeping informations every time a function is called, so that we know where to return to when we encounter the return statement in a function. And now this control returns there, and we continue execution. That is the second invocation of the function power, and this time maybe we have put a large exponent, so power is running a bit more, it is taking a bit more time to run power. And then after we have run power, after we have executed the instructions in power, we are going to execute the return result instruction, and then this bookkeeping information tells us where to return to, and then we execute the subsequent instructions, return from the function myencode, execute subsequent instructions in the function main, and maybe this time when we go back to the for loop, we have to exit from the for loop, so we execute instructions after the for loop and return. Now having seen this animation of how control flows, let us take a closer look at what exactly is happening. The operating system called the function main. I have sort of represented it here by saying that the operating system at some point of time called the function main. The main called the function myencode with two parameters. So I have sort of put that on top of the previous entry that I had kept there, because this is the latest function call that happened. Then myencode in turn calls the function power with some other values of parameters. So now I have put that on top of the previous two entries, because that is the latest function call that happens. So now when power returns, I have to look at the latest function call that happened, and I have to figure out where to go back to in myencode. Specifically, I will go back to exactly the location, exactly the instruction where myencode called power, and after that this entry is no longer needed. Then myencode calls power again with different values of the parameters. So I store that information on top of this stack of information, because that is the latest function call that happened. When power returns to myencode, I have to see what was the latest function call, where was the function invoked, and when power returns, I will have to go back to exactly that instruction where this function was invoked, and then that entry is no longer needed. Now myencode returns to main, so I have to go back and figure out where did my main call myencode, and I have to go back there. After that, that entry is no longer needed, and finally main returns to OS, after which this entry is not needed anymore. So if you look at the way I was managing the information over here, I basically needed to keep track of which function was called, but whenever there was a return, I wanted to access information about the latest function that was called. So I really need to access information in the last in first out order. So that is what we need to do. We need to store information about function calls such that we can access them in the last in first out order. But this is exactly what a stack allows us to do. You can think of a stack of papers. When I put in one paper, it goes to the bottom of the stack, the next paper goes on top, the third paper goes on top of that, and when I am removing papers, I am removing from the top of the stack at any point of time. And then if I want to add some more papers again, it again goes back to the top of the stack, and removing again removes always from the top of the stack. So this is exactly how we want to manage information about function calls. So that is what the computer actually does. It uses a call stack to store information about function calls, and we will soon see that this call stack resides in a special reserved part of the main memory. So now the question is, we know that we must use a stack. What is the information that we must store in this call stack? Now let us recall the flow of control again. We made a function call there, and we kept this bookkeeping information here, and then when we executed this return statement inside myencode, we use this bookkeeping information to figure out where to come back to, which means that I need to remember where to return in the calling function. In addition, after I have returned back here, I am going to execute further instructions in the calling function. So I must also remember what the values of various local variables were in the calling function at the time I made this function call. So this basically tells us what we must store in the stack. Now to understand how it is exactly stored, let us see how the memory for an executing program, also called a process, looks like. Now the operating system is going to allocate only a part of the main memory for use by a process. So if this is the main memory, the operating system may allocate this part for use by our process, and this part is further going to be divided into three segments. The code segment stores all the executable instructions, the machine instructions in the program. The data segment is used for dynamically allocated data. We will see this in a later lecture. The stack segment stores the call stack that we have just seen. Now that you know that a program is actually stored in a part of main memory, so it is easy to see that each instruction of the program which is stored in some location of main memory will also have a memory address. And inside a computer, in the CPU, we use a special register called the program counter that always holds the memory address of the current instruction being executed by the computer. This is very convenient when implementing function calls and returns, because when a particular function is called from another function, all we need to do is we need to note the value of the PC at the time the function was called, we need to save it somewhere, and when we are returning from the called function, we should simply resume execution at the saved value of the PC. So this is how we actually manage information so that we can figure out exactly where to return when a function returns, and this is what is formalized in what is called an activation frame or an activation record. Every time a function is called, we make an entry in the call stack, and this entry is called the activation frame or record. For example, if the main function calls myencode, this is the caller function, this is the callee function, the activation record for the callee will contain memory space for all the local variables of the callee. It will contain space for the program counter value in the caller when the callee was called. So in our case, it will have the address of the instruction in main that called myencode. It will have space for the return value of the callee, and it will have some additional bookkeeping information also. Let us not worry about that. Now once we know that this is the information that is saved in an activation frame which will go onto the call stack, let us see how activation records are used in a call stack. So let us say a function calls another function. In this particular case, myencode calls power. So in the call stack we already have the activation record for main, this was already invoked. Main in turn invoked myencode, so the activation record for myencode is also there, and now myencode is invoking power. When myencode invokes power, a fresh activation record for power is created. The values of all these function parameters from the calling function to the called function gets copied from the activation record of myencode to the activation record of power. The PC value of the caller, the address of the instruction that called this function power is saved here in this yellow thin rectangle here. Other bookkeeping information is updated, and finally the activation record of the callee is pushed onto the call stack. What happens when a function returns? In this case, when the power function returns, its activation record is popped out from the call stack. The return value of this function, here we had a return result, the return value was reciting in the activation record of the power. It will now be copied to the activation record of the caller, which is now on top of the stack. The value of the PC, which was the location in myencode where power was called, will be popped from this activation record and loaded in the PC of the CPU. The activation record of the callee will then be freed up, and an execution will resume exactly at the location given by this updated value of the PC, that is the instruction in myencode where power was called. So in summary, in this lecture we looked at flow of control in function calls and returns. We looked at how memory is laid out for a running program, which is also called a process, and we saw the use of call stacks and activation records in function calls and returns. Thank you.